Okay, and that's time. The answer is D. And I saw some people threw that in the chat. That's great. If you want to throw the answer in the chat, please feel free. You're absolutely not obligated to do so. So let's go through this. And I hope I saw a bunch of people got the right answer, which is great. I hope I caught a couple people on with mistakes. So let's go through this and then we'll talk about sort of the principle. So I like to, even today, I've been doing this for decades now, and I will still draw the diagram every single time I do one of these questions because I just feel like it just makes it less likely for me to make a mistake, and it only takes, about 15 seconds to do. So I have an object, which is an arrow, 10 centimeters from a +5 diopter lens. So that just kind of sets me up. Now, if you haven't seen these kind of questions before, this isn't going to make a lot of sense, so don't worry about it. But if you have, hopefully this is something that you're kind of used to, or at least kind of seen the mechanics of it before. So the first thing I do is I want an object distance. How far is the object from the lens, which is a little u, and distances to the left of the lens we denote as negative by convention. So it's minus 10 centimeters or minus 0.10 meters. And now I need what's called a vergence. Vergence is big U, and that's the light that comes off of the object when it hits the lens. What is it doing? Is it converging, which is positive vergence, or is it diverging, which is negative? And you're going to do this calculation a million times, so it's good to get used to it. It's the inverse of distance. So vergence and distance, always the inverse of each other. Distance in meters, vergence in diopters. So big U is 1 over minus 0.1 meters is equal to minus 10 diopters. Good. So once we get here, and one thing to note, I think, one of the common mistakes people make is that object vergence is almost always, for real objects, it's always negative because light always diverges off of objects, right? If light hits an object, unless it's a mirror or a lens or something very specific, the light will spread out. So big U in most of these questions is going to be negative. So if you get a positive big U, just double check yourself and make sure you didn't just forget the negative. The only situation that typically happens is if you have a two-lens system. So one lens creates kind of a positive vergence for the object, or if you have a mean examiner who just tells you it's that way. But if it's a real object, big U, object vergence is negative. Now that I got that, I just plug it into what is going to be a very familiar equation to anyone who's done a few of these. U plus P equals V. Big U is minus 10. The power of the lens is positive 5. Big V is minus 5 diopters. So that's the image vergence. And then I take 1 over the vergence to get a distance. So the image distance is 1 over minus 5 minus 0.20 meters, or 20 centimeters. And remember, minus is to the left. So by convention, it's to the left. So minus means that this is 20 centimeters to the left. Another way that you can think about this, if it helps you remember, is that image vergence is negative. So that means that light that comes out of the lens is diverging. Negative vergence is diverging. So light is diverging out this way. So the light is never going to meet on the right side hand of the lens. You have to draw imaginary lines to see where it's coming from, so you know it's on the left side of the lens. The last part of it is it real or virtual? There's a couple different ways to think about this too. One of the easiest ways I think for residents is just to kind of memorize it. And that's that real objects are to the left and virtual objects are to the right of the lens. If the object's to the left, it's real, right, it's virtual, and images are the opposite. If an image is to the right, then it's real, and it's to the left, it's virtual. So this image is to the left, and that means it is virtual. So the answer is 20 centimeters to the left and virtual. If anyone did the question and got one of the other answers, like A, B, or C, that's kind of not by accident. So one of my exam tips for you in optics is that when you're writing an exam, you know the most common mistakes people make. So you basically say, some people are going to forget the object vergence is negative. You plug that into the equation, and that's answer A. Some people are going to forget to take the inverse of big V to get little v. And so you plug that number in and you get answer B. And some people forget that virtual images are to the left and real images to the right, and that's answer C. So one thing to be careful of is if you're doing a question, you get the answer. If you happen to make one of the mistakes that we know people commonly make, it could be you got the wrong answer and you'll never know to go back. So that's why you want to be practiced at these and make sure you kind of miss those common missteps. And this is, if you're going to take one thing from tonight, it's this. This is the basic lens formula, U plus P equals V. If anyone who's come to Toric, hopefully you've seen this before. And it's kind of very simple, but it sort of describes everything that we work with, right? This is how corneas and lenses and IOLs work. This is how glasses and contacts work. And partly, I think that's why it's so examinable. And the other reason is there's just so many things we can ask you about. So the object vergence, the light coming off the object, is 1 over the object distance. So big U is 1 over little u. The power of the lens is 1 over the focal length, and the image divergence is 1 over the image distance. So I can ask you about any one of those three, and you have to take a lot of reciprocals to get from distance, divergence, and back. There's also a bunch of other stuff we can ask you about. So I can ask you if the object or image is real or virtual. I can ask you about the magnification, which is big Q over big V, object divergence over image divergence, or I can ask you about the orientation. Is the image upright or inverted relative to the object? So just so many things I can ask you about. It applies to so many things, which is why I think this is, the #1 examinable equation in all of at least geometric objects. Okay, so with that in mind, let's try another one. Question 2. An object is 5 centimeters from a -5 diopter lens. How far is the object from the image, and what is the linear magnification? I'm going to give you another minute or so to do this. Okay, answer is D. And I see, thank you for people answering the chat. I see I caught a couple people out. Next year I should get like an app that people can download to answer the questions in, but anyway, actually, okay, so this is a good question, I think. This is like a classic kind of thing that OCAP people do to you. So let's go through this one. So this one is an object is 5 centimeters from a -5 lens. I'm just going to draw this head again, like I always do. 5 centimeters from a -5 diopter lens. And I want to know how far is the object from the image and what is the linear magnification. So I'm going to go through the exact same process. So little u is -5 centimeters. It's equal to -0.05 meters. Big U object divergence is 1 over little u, 1 over -0.05, which is -20. So I have my big U, which is -20. Now I'm going to plug it into my handy dandy basic lens equation. U plus P equals V. -20 minus 5 is equal to big V. Big V is equal to -25. Little v is equal to 1 over -25 to -0.04 meters. It's equal to 4 centimeters. And remember, minus means it's to the left. So 4 centimeters to the left. Answer is 4 centimeters. Great, right? Problem. I didn't ask you, which is usually the question, how far is the image from the lens? I said, how far is the image from the object? And so this is one of my second hints to you guys is that when you're writing exams, what you're trying to do is basically catch people out. You want to see is anyone, the OCAP is time stressed, you're going through it quickly, and some people just don't read the question or don't have time. So look at the question carefully, because they're going to throw little wrinkles like this and just to see if they can catch the people who are really paying attention versus the people who are not. So the answer is not 4 centimeters, it's 4 centimeters from the lens to the left, but the object is 5 centimeters to the left. So the image and object are 1 centimeter from each other. So the answer here is 1 centimeter. The second part of the question is magnification. This is just a nice simple formula. Big U over big V is equal to -20 over -25. And the magnification is equal to +4 over 5. So 1 centimeter image from object and magnification is +4 over 5. Two other things I could have asked here is the image magnified or minified? And so 4 over 5 is less than 1, so the image is minified. And is it upright or inverted? And because the magnification is positive, image is upright compared to the object. So tricky. Basic lens equation, great one to practice, comes up all the time. Make sure you avoid the common mistakes because that's going to get you the answers on the multiple choice. You'll never know you're wrong. And read the question carefully because there's little wrinkles they're going to throw in just to try to catch the people who are kind of really paying attention from the people who are rushing through or just haven't read the question. All right. Question number 3. An object is 25 centimeters in front of a concave mirror, diameter 2 meters. where is the image? And again, about a minute or so is what you're likely to have for this kind of question. Okay, that's a minute. And if it's feeling fast to anyone, as it probably is, this is a good lesson of why it's important to practice these questions, because you get on the OCAP, I think about a minute a question, or in the Royal College too. So you have about that amount of time for this type of question. Answer is B. So mirrors, let's go through mirrors. So like a whole new ballgame here. So how does a mirror work? Well, again, I'm just going to draw this in because again, that's going to help me. So I have my object here. It's a concave mirror. I'm usually sort of represent mirrors like this, and it's 25 centimeters away. So there's a few things that are similar and different about mirrors. And this question was trying to design to show some of them. So the diameter of the mirror is 2 meters, which means the radius is 1 meter. And that's important because the power of a mirror is technically -2/r. Don't worry too much about the minus. That's just in there for the optics always has conventions. I think if you can sort of memorize that a concave mirror like this is sort of pushing the light together, it's converging things, so it has plus power, whereas a convex mirror is pushing things apart, so it has negative power. That's more likely, I think, to get you the right answer. So technically, in this case, the radius would be -1. But if you just get to the 2 and realize it's concave and say, oh, that's plus, then you're in good shape. So the power of this mirror is +2. So now that I got there, now I just go to my handy dandy basic lines equation. I have u this time is -1/25 centimeters plus 2 is equal to big V. So that gives me -4 plus 2 is big V. Big V is -2. Little v is 1/-2 or -0.50 meters. And here's the other tricky thing, mirrors versus lenses. So in lenses, right, minus means to the left. In mirrors, it's different. So the minus vergence on a mirror, all the light stays to the left of the mirror, right? Light can't get behind a mirror. So the minus vergence means that light is diverging when it bounces off the mirror like this. These rays are never going to meet on the left as in front of the mirror. So you got to draw imaginary lines back behind the mirror. So this minus in mirrors means that it's 50 centimeters behind the mirror. So 0.5 meters or 50 centimeters behind the mirror. And some people are probably asking you, like, why do we ask about mirrors, right? What does that have to do with ophthalmology? So we come across mirrors a little bit, like the front of the cornea is a mirror, but it's not that frequent. And the reason we get asked about mirrors basically is because it's what's called a differentiating question. So the OCAP, I learned this when I finished residency and started writing exams. If you write a question that everybody gets right, it's not that useful, right? It's too easy. Everyone gets it. It doesn't help you determine who studied and who didn't. If you write a question that nobody gets right, also not useful. So the best questions are ones that the people who studied get right and the people who didn't study don't get. So mirrors are kind of perfect that way because they're kind of quirky. You don't come across them all the time, and you really have to sort of study it to get these questions. And that's why a mirror, even though it's not like a very common clinical thing, it's a pretty common OCAP type question, or Royal College as well. So what's different to mirrors and lenses there's some similarities and differences. The similarities are the same basic equation applies. Object vergence big U plus power of mirror P equals image vergence big V. The other thing that's the same is the magnification. Same equation, big U over big V, object vergence over image vergence, and if it's positive, it's upright, if it's negative, it's inverted. The difference is, and there's a couple key ones, are the power and whether the image is real or virtual. So for the power, it's 1/the focal length, that's the same, but for mirrors, you can use the radius. So it's 2/r, or technically it's kind of -2/r. The minus though is just for convention. I think it's easier to memorize that if it's a concave mirror, it's pushing light together, it's a plus power. If it's a convex mirror, it's pushing light apart, it's a negative power. Opposite of lenses, right? Like a minus lens is concave. So a concave lens has minus power, concave mirror has positive power. A convex lens has plus power, convex mirror has negative power. The other thing that's different from mirrors is the real or virtual image. So the object is the same for both mirrors and lenses. Object left, real, object right, virtual. But for mirrors, the image is different. So for mirrors, object and image are both real if they're in front, and both virtual if they're behind. So real to the left, virtual to the right. Whereas remember, for lenses, it switches. So for lenses, it's object left, real, right, virtual, image, right, real, left, virtual. So that's a lot to wrap your head around. That's probably why mirrors are a good question, but good, I think, to do some of the practice questions on mirrors, just so and they're gonna almost for sure hit some of these differences to see if you know it. Okay, so I started the start of this lecture with the heavy calculations thing, so we're gonna keep rolling with some of the stuff. So question number 4. My friend Edsel is a myope who wears minus 25 glasses at a vertex distance of 10 millimeters. What power of soft contact should you prescribe? Minus 15, minus 20, minus 25, and minus 30. Sorry, I see a question in the chat, but I'll probably circle that on the break if that's okay, just so we kind of keep rolling through. So, all right, so this is a vertexing question. So let's see how we do it. And the answer in this case is B, minus 20. So there's no right way to do this. One of the nice part about optics is that unlike, say, high school math, there's no marks for work. So if you have a different way of getting this, and I've seen all kinds of interesting, unique ways of residents getting answers over the years, it's totally fine. So I'll show you my way, but there's no like sort of correct way that has to be done. So vertexing is basically taking a lens from one place and moving it somewhere else and finding the equivalent power. So in this case, I have minus 25 diopter glasses here. I have an eyeball here, and I want to move it here to here and say, what's the power I need? So it's an equivalent power of contact. The way I do it is I say, okay, well, where's the secondary focal point? Which means that when light from infinity goes through this lens, where does it focus? And the focal point for this light hits the minus 25 diopter lens and diverges. And how much does it diverge? Well, handy dandy reciprocal, 0.04 meters or 4 centimeters. And because the light is diverging out of this lens, the secondary focal point is over here. So it's 4 centimeters to the left of the lens. That's the secondary focal point. And then I say, okay, well, how far is that focal point from my new lens? So that I get rid of that minus 25 diopter lens and say, okay, it's 4 centimeters from that where that lens was, plus another 1 centimeter, 10 millimeters to get to the cornea. So the focal length from that focal point to my new lens is 5 centimeters in this case. And then the new power is the reciprocal of that distance. So 1 over 0.5 is 20. And it remains the same power, minus 20. So that's a very useful skill to have. This comes up all the time. Basically, vertexing and moving lenses one way or the other. One thing that you may find this useful or maybe not. So if you don't find it useful, please just ignore this part of it. But sometimes in the OCAP, you just run out of time and you don't have time to do the calculation. And so you just have to guess. One thing you can do to help you guess is that you can at least be directionally correct. What I mean by that is that if you kind of do enough of these questions, you sort of intuitively realize that when you're taking minus lenses and going from glasses to contacts, moving back this way, it's less power. So a minus 25 glasses, minus 20 contacts. Opposite for plus lenses. So if someone is an aphakic, they have contact lenses of like plus 12. Whereas when you replace their lens, it's like plus 20 or 21, right? So as you move back in a plus lens, you need more power. So if I see this question, I literally have 5 seconds left on the exam. I say, okay, I'm minus, it's moving it back. It must be less power. At least that gives me the choice between A or B. Also, is a way to double check yourself after you do the question. So if you answer this question and you got minus 30, and you can just double check yourself and say, oh, if I take a minus lens going backwards, it should be less power. You know you've just made a mistake in the calculation. So it's a kind of a cool way to take at least a better guess than 1 out of 4, and then a way to check yourself too when you're doing these types of questions. So vertex. So this is glasses to contact, or you can just take a lens and change the vertex distance, all sort of the same process. And this is, again, my 3 steps, but you don't need to memorize this, just figure out a way that works for you. First, find the secondary focal point of the old lens. The focal length of the new lens is the distance from that lens to that focal point. And then the power is the reciprocal of that distance. So why don't we try another one? See how we do in vertexing. Oh, good question. Someone said by convention, should you put the eye on the right side? Good question. So just quickly, when in lens questions, almost always by convention, we have like an object on left lens and then image going to the right. For vertexing, it doesn't. No such convention. So you can kind of put it however makes sense to you. I tend to go left to right just because that's how I do all types of questions. Okay, give you another 45 seconds for this one. I'm very impressed at the speed of some of you guys. Amazing. Okay, and that's time. The answer is B. And now, again, if I had 5 seconds left on the OCAP section, I needed to guess. I'm taking a plus lens and I'm moving it further away. So let's say taking an IOL and moving it to an aphakic contact lens, right? It should be less power. So at least I know it's A or B. Now, probably better to just calculate it out. So let's do that. So we have plus 10 lens here. My eyeball over here. And I want to move that to a vertex distance of 20. So out here. So this guy is 20. This is 10. So again, I'm just my same 3-step process. It always works for me. Light hits the old lens and it's going to converge. And I want to know where is that focal point? And it's 1/10. Secondary focal point, 1/10, 0.10 meters or 10 centimeters to the right of this original lens. And once I know that, I can kind of forget about that lens, right? So I know it's 10 centimeters back here. I'm just going to kind of erase that. Don't need that anymore. So it was 10 millimeters to here, and then it's 10 centimeters secondary focal point. Now I need that total distance from the focal point to the new lens, which is going to give me 11 centimeters. And then I take the reciprocal of that, 1/11, gives me like 9.1-ish or something like that, or approximately plus 9 diopters. So that's vertexing. Another thing that comes up almost every single OCAB and Royal College in some fashion. So just however you do it, no marks for showing your work. Just figure out a way you can move one lens to another lens, get the right power, and also if you can know directionally which way to go, that I think that'll help you to help avoid some of the more common mistakes. All right. Okay, put down our pencils. We'll do we'll kind of do 3 conceptual questions to give your frontal lobe a little bit of a break here, and then we'll get to 10 and take a little break. Okay, which light phenomenon limits pinhole resolution? Scattering, diffraction, refraction, or reflection? Give you like 10 seconds to think about it. And it looks like people pretty good at this one. Diffraction. So this is the section of optics basically is like physical light phenomena, like how light behaves in the real world. And as opposed to calculations, this tends to be more conceptual stuff. So let's go through some of the more common ones that get asked about. One of them is scattering. So scattering is the redirection of light due to interaction with particles. This is what happens in the atmosphere. Light hits air particles and scatters. So light's right above, blue scatters, and that's why the sky is blue during the day. And at the sunset, the blue light has scattered out, and all that's left is red. So scattering is what makes the sky blue during the day, and sunset's red at night. Also, when the kind of cornea becomes edematous, the fibers lose their regular structure, it scatters the light. And that's why an edematous cornea is opaque. Two is polarization. So light waves have electrical and magnetic fields that oscillate perpendicular to each other, and we sort of, just by convention, say the orientation of the electrical field is kind of the polarization of it. Unpolarized light just has random orientation. It's kind of all around. But if you pass it through a polarizing filter, then you get polarized light. It's all oscillating in the same orientation. This is how polarized glasses work. They basically filtered out the kind of polarized light that tends to bounce off of things like glass and water. Also, how 3D glasses work. They polarize them in opposite directions. So your right eye gets one image, your left eye gets a separate one. And also the retinal nerve fiber birefringence is polarization of light. Interference. Interference is when light waves overlap and they can constructively interfere. So you get like a greater peak or trough, or destructively interfere, you get less. This is how anti-reflective coating works. You see the glasses on the left do not have the coating, and the glasses on the right do. And you basically put a quarter of a wavelength thick layer. And so the light that bounces off the front and the back of that layer are exactly half a wavelength out of phase, and so they destructively interfere and cancel each other out. It's also amazingly the way OCT works. So OCT bounces light off the eyeball, have a reference mirror, and uses the interference pattern to create amazing images. And then diffraction. And diffraction is this kind of cool process where light will bend at a corner or aperture. These waves come through this little aperture, then they don't go straight through, they bend. So as the pinhole gets smaller, the blur circle decreases, but it gets too small and the light starts to diffract. And that's what limits the size or resolution of a pinhole. Okay, that's light phenomenon. Another conceptual question for you. Which light phenomenon is greater for light with longer wavelengths? Is it scattering, diffraction, refraction, or reflection? And again, conceptual questions, so I'll just give you like 15 seconds to think about it. All right, answer. Again, nice to see some familiar names in that chat, is diffraction. So another sort of quick but high yield optics concept are there certain things that will change depending on the wavelength. Two that are greater for shorter wavelengths and one that's greater for longer wavelengths. And I don't know if you can sort of rationalize this out. It's one of those few things in optics that's probably just good to memorize. So one is refraction. So things will refract more with shorter wavelengths. That explains rainbows, right? Light goes through a prism. The shorter wavelengths like blue refract more than the longer wavelengths, and the light separates out and you get a rainbow. Also explains chromatic aberration. Scattering, where we talked about scattering from the sky, also more with shorter wavelengths, and that's why when the sun is right overhead, the blue light, the shorter wavelength scatters more, and that's why the sky's blue. The only one that's longer with longer wavelength is diffraction. And so things with longer wavelengths will diffract more than things with shorter wavelengths. All right. And I got one more conceptual question for you, and then we'll do a couple calculations and take a break. Which of the following is a property of laser light? Okay, good job. Coherent. So laser light I threw in here because it kind of overlaps a little bit with the light phenomenon stuff. And this is probably my busiest slide, but I wanted to chuck in all of the stuff that will get asked about lasers commonly on OCAP type exams. One is, interestingly, what laser stands for. That's been on there a few times. The properties of laser light, and then the mechanisms and the corresponding types of lasers that we use. So what does it stand for? It stands for light amplification by stimulated emission of radiation. Very interestingly, people have invented three other things that sound like laser for a good multiple choice question. So make sure you've just seen that short form before. Five properties of laser light, and I kind of think of them as two that a 5-year-old would know, and then three kind of opticsy principles. So, if you asked a 5-year-old what is a laser, they'd say, well, it's super powerful and it goes straight in a direction. And that's so high intensity, unidirectional. The other three are kind of like these opticsy principles, right? It's monochromatic, so it's a single wavelength. It is coherent, or it's in phase, and so there's constructive interference, and it's polarized. So unidirectional, high intensity, like you're shooting a laser gun, and then monochromatic, coherent, and polarized. And then there's the 5 mechanisms and the associated lasers. This used to be 3, and then the AO manual added 2 more just recently, so now you gotta know 5. And it's a bit kind of annoying because PDT I don't think anyone really uses anymore, but anyhow, in the book, so you got to know it. So the 5 mechanisms, there's photoactivation. That's when a laser interacts with a photosensitive dye, which is like photodynamic therapy. I think it used to be a treatment for AMD. Don't think it's used too much anymore. There's photocoagulation, which is like burning it, or thermal interaction. And that's like you're burning around a retinal tear, and that's your argon and krypton lasers. There's photoablation, which is breaking covalent bonds, very precise process. And that's the excimer, like that famous image of cutting a hair very precisely in like a fortification phenomenon. And then there's 2 that used to be 1, and they kind of split them, but they're very similar in terms of the mechanism. So a photo disruption is shockwave generation, like little explosions, right? So like the YAG laser, when you're blowing up the posterior capsule, and SLT, that's photo disruption. Very similar concept. Plasma-induced ablation is stripping electrons, and that's the femtosecond laser, which we use in refractive surgery and in cataracts now. So bit of a busy slide, but I think the 3 kind of things that are commonly asked about lasers, what it stands for, properties, the tissue laser interaction, and the types of lasers. All right. Now I thought I'd finish off with a couple of quick calculations, and then I think we'll all take a 5 or 10 minute mental break and see who can make it enough energy to come back for the second half of this. All right. Kamiar is wearing a monocle of -1, +7, axis 90. What is the minus cylinder form and spherical equivalent of this lens? Give me a minute. All right, so this is very impressive. People are getting these questions in like 20 seconds. It's amazing. I think the residents are much smarter than back in my day. All right, and as I think a lot of people got, answer is C. So this is the basic lens stuff. Hopefully you have seen this in clinic. If not, it's a very useful clinic skill to have. But this is basically switching from minus cylinder form to plus cylinder form and spherical. So this is the plus cylinder form because the cylinder is in plus. And if I want to switch it to minus cylinder form, first I add the sphere and cylinder together. -1 + 7 gives me +6. I switch the sign of the cylinder, so now it's a minus cylinder. And I flip the axis by 90 degrees. That's the minus cylinder form. Spherical equivalent is equal to the sphere plus half the cylinder. So that is, in this case, is -1 plus 7/2 -1 plus 3.5 gives me plus 2.5 diopters. So not only is this a good exam question, but it comes up in clinic a lot, right? Like we use plus cell often, and optometrists use minus cell, and so you just want to be kind of quick at this. Or if you're going to give someone, if you want to start refracting and you have the glasses, the spherical equivalent is a good place to start. And so this is kind of my lens basics section. So this is a 3-step process going from minus to cylinder forms. Every lens has 2 equivalent forms. One is a plus cylinder and one a minus cylinder. And it's 3 steps, which takes you back between the 2 different forms. So if you're going to switch the new sphere, you just add the sphere and cylinder numbers together. The new cylinder is the same number with an opposite sign, and then you change the axis by 90 degrees. And the spherical equivalent is the sphere plus the cylinder divided by 2. Okay, and now this gets us to our last question, the first half of this thing. So Camrier went and got himself a new monocle. It's now +2 -3 axis 180, and I want to know which is true. And this is I think, be a more kind of typical OCAP-y type question. So I'll give you a minute for this. Okay, answer is A. And I think maybe I caught a couple people out there, so let's go through this one. So I have a single lens, +2 -3 axis 180, and I've given you a bunch of things about it, and I want to know which one's true. And this is where you have a minute to do this. So you have to be quick at kind of getting these sort of characteristics out. So the first thing I'm going to do is say, okay, well, I'm going to switch the form. So it's +2 -3 axis 180. What's the plus cylinder form? I add the +2 and the -3. That gives me -1. I change the sign, -3 becomes +3, switch the axis by 90 degrees to 90. So I think that was the plus cell form. So that was one of the wrong answers. Okay, so I'm going to now do the spherical equivalent. Spherical equivalent is the cyl for the sphere, +2 plus half of the cyl. So -2, sorry, +2, apologies. +2 minus 1.5 gives me +0.50. So the spherical equivalent is actually positive, and that's what makes it's not a myopic astigmatism, because the person is overall a hyperope. And the final part of it, and I think this is where people get messed up, is I need to be able to convert this spherocylindrical lens to two simple cylinders. And you can either represent that as an axis cross, which is represented by a little x, or a power cross, which is represented by the kind of the email sign. So again, no marks for work, but this is how I do it. But you have to, as part of a question like this, or sometimes just to get to another part of an answer, and you'll see that when we get to the Prentice rule, you have to be able to do this pretty quickly. So the way I do it basically is I'm going to break these both down into axis crosses, the sphere and the cylinder. So a +2 sphere can be broken down into +2 and +2. If you have two cylinders which are 90 degrees apart with the same power, that's the same as a sphere. Those two are equivalent. And then the -3 axis 180, I'm going to break that down into a -3 axis 180. And then I can just add these two together to give the two different cylinders in axis cross form. +2 axis 90 -1 axis 180. Now, tricky, I didn't ask you about the axis cross, I asked you about the power cross. And so the power cross is just you flip the axis exactly 90 degrees. So for the axis cross, it's -1 at 90 +2 at 180. And so that's the way that you break down a spherocylindrical form into two cylinders. And you have to be able to go back the other way too. Take two cylinders and go to the axis cross. So I think the answer in this case was that +1 at 90 and +2 at 180. Okay, that was great. We did pretty well time on that, and that was a bit of a whirlwind. I think. Oh yes, my last exam point is this sort of you want to be able to kind of circle this thing quickly and accurately. So Most lenses are in a spherocylindrical notation. So you want to make sure you can go to a power cross, an axis cross, and back again. And you want to be able to flip between plus and minus cylinder forms and calculate the spherical equivalent. And these things, in an average exam, you'll have like, I don't know, 15 or 20 seconds to sort of do it if you want to keep within your time limit. And so just practicing these and make sure you don't make like little mistakes on this part of it, I think can be super useful, both to get the questions right and to save you time on the exam. Okay, so that was heavy. You guys are great. Thanks for participating and sticking around. I think we need a full, I don't know, take an 8-minute break, 8-minute break, and we'll come back and I got 10 more questions, hopefully a little shorter on the far side of this. So I got 8:19. Let's come back. If we could reconvene about 8:27, that would be great. And so I saw some questions in the chat. I'll back up and I'll stick around in case if I can answer any of these questions as we go.
Yeah, great job there, Mike. You're one of the few lecturers where the number grows as the lecture goes on. So great job.
People wake up. It's past my bedtime, that's all I gotta say. I'm impressed that anyone's awake to it. Okay, so yeah, so anyone wants to go to washroom break or get a snack, please do. I'll start the second half of this and we'll do 10 more questions at 8:27. And I'll stick around if anyone wants to just unmute themselves and ask me questions, or I'll pop to the chat and see. Looks like some of my thank you, Prem. Some helpful residents are answering some of the questions for me, which is great. Thank you.
Hey, thank you so much. I'm still a little confused about that, the second vertex question. I
Sure.
thought I thought we always basically add more power as we come closer to the eye. Um, and so if they were a minus 10, or sorry, a plus 10, then you'd need more power because you need to like converge more because you have less distance to converge.
Yeah, it's a good. I see you're trying to think it through conceptually. It's interesting because it goes plus and minus are different, and it's when you think through that, it's going to be a bit confusing. So let's just go through it mechanically, and then we'll see if it makes sense. Is that okay?
Sure.
So I got a plus 10 lens diopter here, eye here, and in this case, I'm moving it this way, right?
No, you're moving it towards the eye. Oh, sorry. Was the question they were wearing
Yes.
contacts?
So the question, interestingly, was just changing vertex distance, and I put it in there specifically because it's
Oh,
kind
I
of a
see.
weird
Okay,
one.
okay.
It doesn't
Okay.
get asked that much. So you're exactly right. If you're going this way to contacts, it would have been the opposite. It would have been a smaller number, would have been plus 11. Right? As you go, as plus gets closer to the eye, you need more power. But in this case, I moved it from 10 to 20
Oh,
millimeters.
okay. Yeah, yeah, yeah. Okay, never mind. Then it told I honestly just didn't read the question. I thought we were going to contact lens. That makes sense.
No, totally. What you did is exactly what everyone does, right? You jump into the automatic mode,
Yeah,
and
yeah.
it happens so often. So it's funny when you get to the OCAB. One of the most important things with optics is you just got to read through because they're trying to trick you, right? They're trying to ask you something in a way that you're not used to seeing it. And that's how they kind of catch people in because you go and you automatically do what you always do, and you do it correctly, but they've changed something in the question that made that's just kind of odd. And so they catch out people who are trying to go too fast or just didn't quite have a chance to read it through carefully.
Yes, 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 yes. Okay, okay. Yeah, that makes more sense now. Thank you. And then sorry, we said the answer to 3 was B. I was driving, I missed that part too. But I
We can
think you
go all
said
the
it
way,
was B, right?
back to question 3.
Yes, the concave mirror.
Mirror questions. B, yes, 50 centimeters
B.
behind.
And it's just by default minus 2 over R?
Yeah, it's interesting. So with lenses, the if you have a single surface, it's like you take into the refractive index, like n over r, right?
Yeah.
With mirrors, because it's a single surface, there's no refraction, it just bounces. The way the math works out, it just ends up being like 2 over r. So that's just all the if you have a radius for a mirror, the refracting power of the minus, and the minus is just there for convention, but if you just know that this is plus and this is minus.
Okay. Okay, perfect. Thank you.
No pleasure. Okay, I see someone asked about the first vertex one, so let's do that. Which vertex one is this? Oops. Okay, so I hope the person asked that question is here, but let's do this first vertex question, which is question 4. So we're going from minus 25 glasses at a vertex distance of 10 millimeters to contact, so to the corneal plane. So I have my minus 25 glasses here. And I want to move this 10 millimeters to the corneal plane. And again, and there's kind of multiple different ways to do this. So if anyone's learned different ways or does have a way to work for them, it's totally fine. But kind of the way I think of it is this: the light. What you want to basically do is focus light from infinity, right? That's kind of how we're correcting people. And so what the lens does is it takes light from infinity and focuses it on that person's far point, basically where you're in focus when you're trying to look into the distance. Right? So if I'm a -1 mile, I'm naturally focused at a meter away. And so my lens has to take light from infinity and put it at that meter so it's clear for me. That makes sense. So what I'm first going to do is say, okay, light comes from infinity. Where does it focus? Where is this far point for the person? So it hits this lens, it diverges. And where's the focal point? Well, it's diverging. It's never going to meet sort of on the right side of the lens here. You have to draw imaginary lines back. How far back? Something we do all the time in reciprocals is take reciprocals, sorry, and the far point is 1 over the power. So in this case, 0.04 meters, or the far point of this eye is 4 centimeters to the left of the lens. So here's the far point of the eye right here. Now that I know that, now I want to get rid of these glasses, right? Because this person doesn't have glasses anymore. Instead, what I want is to give them contacts. So this is their far point right here. And when light hits their contact, I need that to focus exactly at the far point, right? That's where they're naturally in focus. And how do I find the power? Well, I take exactly the reciprocal of the distance. So the total distance here is now 5 centimeters from the eye to the far point. And so I need parallel light to hit this, and for this lens, this contact lens, to focus it right there. To do that, the power of the contact is 1 over that distance, which in this case is 20, or minus 20, because it's the same power as the glasses. So again, multiple different ways to do this, but the way that I find most useful, where's the secondary focal point of the lens? So light hits the lens, where does it focus? That's the far point of the eye. And then you measure the distance from that far point to the new lens, whether it's at the corneal plane, if it's a contact, or it can be anywhere. Reciprocal, that distance is the new power. But yes, for pinholes, yes. So a pinhole, as you get smaller, the reason it makes things clear is it decreases the blur circle. So if you're out of focus, there's a blur circle around things, and as you start to pinhole it, that blur circle decreases, and so the letter gets sharper. But as soon as you get too small, then the diffraction starts to happen, and it starts to sort of make the image not in focus anymore. So that's exactly right. As the pinhole gets smaller and smaller, it gets clearer, and then it gets too small, and diffraction takes over, and it gets blurry again. And I think the exact number is like, there's no way to calculate this. Someone just figured it out. It's like 1.2 millimeters is the exact size where the blur circle is kind of optimized before diffraction takes over. Otherwise, you think you could just go infinitely smaller and be clearer and clearer, but diffraction is what makes it, as you get smaller, it actually start to lose the improvement. Yeah, mirrors. Mirrors are such a tough question. So let's go through the mirror thing. I think it's probably worth it, and then we'll start the last half of it, and then I'm happy to stick around to the end too and do some more questions. So mirrors are so tricky because they're like lenses, but they just have these like slight differences that are really annoying. So we just sort of talk through this conceptually to see if this helps at all. So I have this concave mirror like this. And you see, if light hits this, it bounces together, right? It is bringing things together. So it is plus, it's converging. It's like a plus lens brings things together like this. So a convex lens is plus because it brings things together. The concave mirror is positive because it pushes things together. So that's the first thing I think is important to understand for the question. Second one is the power. So diameter is 2, radius is 1 meter, and power is -2 over 1, or +2. So there's the second thing. So the first thing is to understand it's plus power, and the second is to make sure you calculate it as 2 over r, where you get +2 diopters. So it sounds like hopefully people have got to that point. Now the part of like, why is it in front or behind when it bounces off the mirror? So this light comes off the object, and divergence of the object is -1 over 0.25 is equal to -4 diopters. So light that leaves this object is diverging at -4. The mirror is positive, so it's +2, but it's not enough to bring so it's diverging less, but because it's diverging by 4 and you're only adding 2, it is still diverging when it comes off the mirror. So U plus P equals V. This is -4. The mirror tries to converge it, but it's not powerful enough. And so when the image light comes off of it, it is still diverging. And light passes through a lens, right? Comes to the side, but for a mirror, it bounces back. For a mirror, all the light stays on the left. So when it hits this, it is still diverging at -2. That means that the light is never going to come together in front of or to the left of the mirror. You have to draw imaginary lines backwards to find out where the object is. And so that shows the image is behind the mirror. And it's confusing because in lenses, minus means to the left, but in mirrors, a minus distance actually means it's behind the mirror. So the convention is different, or if you can just kind of think about it's diverging, so it's not going to come together in front of the mirror, it's going to come behind. That works too. But that's the difference. So it's -1 over 2 minus 0.05. If this was a lens, that would mean it's to the left of the lens, but because it's a mirror, it's instead of diverging to the right, so you draw imaginary lines back to the left like a lens, it's diverging back in front of the mirror, so you have to draw imaginary lines behind the mirror. So that's why in this case, 50 centimeters behind. And it's just one of those little tricky things that makes mirrors a little bit different than lenses, which makes it such a good exam question.
And the object, that one doesn't change. The object being to the left stays as negative. It's only the image that changes.
Exactly right. So for the object, it's exactly the same. So object to the left, minus divergence, it's real to the left, just like a lens. The object is exactly the same. It's only in the image where it flips. So now the image, the minus distances mean it's behind the mirror, and it's real to the left or virtual to the right. Okay, so 8:30. Why don't we, hopefully people have a chance to go to the washroom, take a little nap, come back. I got 10 more questions. And I think we should be able to make it through, hopefully not too late. And so, all right, deep breath. Get your OCAT brain on. All right, question number 11. Doing encyclopedic retinoscopy, you get neutrality with a +1 diopter lens in all directions. The working distance is 2/3 of a meter. What is the person's refraction? I'm going to give you 45 seconds because this one's a little simpler. Oh, speed demons in this group. Yeah. Okay, answer is it's 50. And this is interesting because if you've done any work in PEDS, you do this process over and over and over again, and you just kind of do it automatically. But sometimes it's hard to take a clinical skill and write a multiple choice question about it. Like that just translation is tricky. And so these questions are often a little bit awkwardly worded. And it tricks people up, I think, because of that, not because they don't get the concept, because they mostly do. It's just that they kind of get mixed up in the wording. So try to start with something relatively simple. So you're doing refraction. Again, the way I think about this is I just write down the lens I get. So in this case, I'm getting +1 everywhere. But that means that they're focused +1 where I am, not at infinity. And so I have to minus my working distance. So in this case, my working distance is 2/3 of a meter. What you minus is the reciprocal, right? Remember, distances to diopters are always reciprocals. So you have to minus 1.5 diopters. So in this case, I get minus 0.50 diopters and minus 0.05 diopters. And two cylinders of the same power that are perpendicular, it's just a spherical lens. So minus 0.50 diopters. So this is cyclopetric refraction. This is anyone who's a DOC knows the kids, right? Oh, love it. This is only like semi-relevant, but it took me like a week to make these diagrams, so I like to try to show them off whenever I get a chance. So if you haven't done retinoscopy before, this is going to make no sense to you, and don't worry about it. If you have, hopefully this is just reinforcing some concepts. So a cyclopedic retinoscopy, we're trying to get someone's refraction, either a kid or an uncooperative dog, something like that, and you flash this thing up and down. And what you're looking for is the reflex in the pupil. And if it's moving in the same direction as you, it's called with movement. This means that the person's far point is behind you, and you have to have plus lenses to try to get that far point right to where you are. If you shine and you get the pupil reflex moves in an opposite direction, that's called against motion. And that means that the person is focused, their far point is in front of you, and you have to add minus lenses to push it back to you. And then if you are exactly perfect, you have them in great focus, you get this perfect kind of uniform lighting up of the pupil called neutralization, which never ever looks this good. But this is your endpoint, and it means that the person is now focused right at your pupil, right at your retinoscope. And then if you want to give them glasses, you don't want them focused right where you are, right? You want them focused at infinity. You subtract your working distance from the lenses that you get. So that was just to show the concept. This is much more likely what you're going to get on the OCAP exam. So let's try this one. So question 12, doing cyclopedic refraction, retinoscopy, you get neutrality with a -1 diopter lens sweeping vertically with a horizontal beam, and a +5 diopter lens sweeping horizontally with a beam that is vertical. Your working distance is 50 centimeters. What is the refraction? This is more like a minute type question, so give this one a shot. All right, I know that probably felt a bit fast, but that's really all the time you gotta have for one of these. And it's so frustrating, right? Like it's so awkward. You do this all the time, and I see people in the exam kind of up and down. You're like, why is it so worded so awkwardly? So let me take you through this and try to find some of the pitfalls that people get trapped in. One is just the way. So the answer to this is A. So let me show you how we get there. One of the weird things about this is just the orientation is awkward, right? Because when your beam is horizontal, you're sweeping vertically, right? So those are one's horizontal, one's vertically. It's sometimes hard to know which is. And if their exam writer is good, which the OCAP ones are excellent, they have to be very specific because there isn't a convention. You can't just say you're sweeping vertically because that doesn't, is your beam vertical or are you sweeping vertically? So they'll usually say your beam's oriented this way or you're sweeping this way, and they'll make it clear to you somehow, but just be careful of that because that often gets people kind of mixed up. And the other part is that they'll often do is they'll change the working distance because most people's arms are about 2/3 of a meter. So they're going to make it 50 centimeters or a meter and a half, something that is no one's arm is, just to see if you know how to make that calculation. So this is the way, again, I do it. If you have a different way of working it through your head, that's totally fine. But I sort of say, I'm going to use the beam orientation, and that's going to give me the axis cross of the glasses. So if not the way you're sweeping, but the way your beam is oriented is equal to the axis cross of the glasses. And that's how I've kind of been doing it for the last 15 years and works pretty well. In this case, the first thing, my beam is horizontal and it's -1. So I'm going to put -1 at the horizontal beam there. And then when my beam is vertical, it's +5. So even though I'm sweeping vertically, my beam is horizontal. So I'm going to put that on the horizontal part of the axis cross. And then I'm sweeping horizontally, but my beam is vertical. So I'm going to put that on the vertical part of the axis cross of the glasses. Now I've got to subtract my working distance. And again, the OCAP is never going to give you what you're used to using. They're going to give you something else. So in this case, 50 centimeters, I have to take the reciprocal of that. And so 1 over 0.5 is 2. So in this case, instead of minusing 1.5, which is what you're used to doing, it's going to be -2. So now I'm going to take that off of both. So +5 becomes +3, -1 becomes -3. And this gives me the axis cross of the glasses. Now here's the part where, remember that lens basics things where you got to go from 2 cylinders to sphere cylindrical notation and switch. This is where it becomes super useful because this is all one question, and now I have to calculate it, take off the working distance, convert this into sphere cylindrical notation, and sometimes convert it from +cil to -cil in about a minute and a half maybe. So again, there's a bunch of different ways to do this. I can take you through it if you haven't seen it, but basically this is going to be -3. And then I have to add 6 to get from -3 to +3. Axis 90. So I get there, and then I look in the answers, and I say, oh dear, I don't see -3 + 6 axis 90. Maybe I did it wrong. Except remember, there are 2 forms to every lens, and so this is exactly equivalent. There's a minus cylinder form, which becomes +3 -6 axis 180. And there's my answer. So this is the type of question you're likely to see on the OCAT because they know that people are going to get tripped up in the orientation, they're going to get tripped up in the working distance, they're going to get tripped up in making the sphere cylindrical notation, and they're going to get tripped up in switching from a +cil to a -cil form. So it's like almost like a perfect exam question, and one where you can probably, if you're not used to it, spend 5 or 6 minutes on it and still get it wrong. And so a good one, I think, if you can get through this question, then cycloplegic refraction, you've got it nailed. Okay, let's switch concepts now to prisms. So Asim, question 13. Asim has a +2 diopter monocle and he reads 5 millimeters below the optical center. I want to know what is the induced prism and in which direction does the virtual image shift if you're looking through the prism? Again, I think about a minute, I think. All right, so a bunch of right answers in there, so nicely done. Answer for this one is B. Let's go through this. So, Prentice rule and prisms, another tricky concept, really good exam question. So I'm going to draw this lens out. So this is a plus lens. Technically kind of looks like this, but when you draw it out, I think it's more useful to draw it in kind of prism form. Like the fat part is the base of the prism and the skinny part of the lens is the apex. So plus lenses look like this and minus lenses look like this. So if you draw it out as a prism, I think that's a good first step. And the power here I got is +2. Next thing I got to know is, well, how far am I from the optical center? And I'm 5 millimeters. So optical center is here. This is 5 millimeters, light going through. And now I use this thing called the Prentice rule, which I'm going to take you through this equation, but it's a really weird equation for a couple of reasons, and we'll talk about that in a sec. But it's the distance from the optical center times the power in diopters. In this case, the distance is 0.5 centimeters times the power of 2 diopters, which gives me 1 prism diopter. So induced prism or prism in general are measured in prism diopters. Which direction? By convention, we always do it in the direction of the base. I think that's kind of, if you looked at a prism like this, you'd say that's kind of how it's built, sort of base, so to speak. So in this case, it is 1 prism diopter base up. So that's the first part about prisms. The Prentice rule is a confusing equation. Second thing is how the image shifts. So I have a prism like this. It physically bends the light towards the base. I sort of think of that as BB. bends towards the base. So if I had a real image going through prism, bends up towards the base. But that's not what I asked you. What I asked you was kind of a sort of a tricky question in that if let's say I'm looking through this. So here's me looking through my prism. My brain doesn't know that the light bent. It just kind of assumes it came straight. And so your brain extrapolates it's down here. And so the virtual image shifts in the opposite direction. It actually shifts towards the apex. So in this case, it's a one prism diopter base up prism. It's physically bending light towards the base. So if you take a laser and shine it through a prism, it bends towards the base. But if you look through a prism, your brain assumes that light has come straight, and so the virtual image shifts towards the apex. So in this case, it's one prism diopter base up, virtual image shifts down. This is the Prentice rule. My mentor, David Hunter, thinks that this is the yes, Edsel says I think it is the only one that uses centimeters, which is why it's so weird. David Hunter thinks this is the most examined equation. I think it's probably secondary to the basic lens equation, but either way, it's a high yield one. It's the Prentice rule, which is induced prism looking through lenses. And the technical sort of equation is the induced prism in prism diopters is equal to distance from the optical center in centimeters times the power of the lens in diopters. And then there's not plus or minus. The orientation is always the direction of the base. So you draw the lens, and if the base is up, down, in, or out, that's how you say how it's oriented. Three things about this that make it weird. And this is why, again, makes it very examinable. One is that prism diopters and diopters are completely different things. I don't know why they name them that way. It just makes it confusing. A prism diopter is like how much a prism deviates light, measured in centimeters at a meter. A diopter is like the power of a refracting or reflecting surface, which is measured in 1/meters. They're completely different things. People get that messed up. Second one is in centimeters, which is again really strange. Right? We never use centimeters for equations except in the Prentice rule. And so they're always going to give it to you in meters or millimeters just to see if you know that it's supposed to be in centimeters. And finally, the orientation is like towards the basis trim. So you have to know where's the optical center, what type of lens is it, and am I above or below to know is it base up or base down. All those things make it tricky. So that first one I think was a little bit more of an easy question. This is going to be more of your OCAP type questions. Question 14. Shrif is retiring to pursue a radio career, and on air he reads 1 centimeter below the optical centers of these glasses. -10 plus 1 axis 90 in the right, -8 plus 3 axis 180 in the left. What is the induced prism? This one might be slightly harder than a regular OCAP question, so I'm going to give you a minute and a half on this. See if you can fight your way through it. Well, thank you for Celia for posting that little diagram from Flint. That's cool. Prisms. All right, answer is D. If you didn't get that or got lost in the way, don't worry about it. This is a tough question, but this is the level you want to get to because this is going to be basically, I think, like right in line with OCAP Royal College type questions. So when you're doing these questions, the first thing you have to do is convert the lenses into power crosses because the power in the direction you're going is what you're going to use for the Prentice rule. So again, multiple different ways to do that. You just got to be able to do it. And so again, if anyone hasn't done this, I can sort of take you through it or you can sort of look it up, but you have to be able to go through sphere cylindrical quotation to a power cross pretty quickly. And so the power crosses in this case The right eye is going to be -10, -9. And the power across the left eye is going to be -5 here and -8. Now, once you get there, I'm saying, where am I relative to the optical center? In this case, I'm below. So I'm going to draw that. This helps me again. I'm going to draw the prism in to see what it looks like. And now I can throw away the horizontal power. I don't care about that because I'm only going up and down. And so I use the -10 in the right and the -5 in the left. And the induced prism is equal to H times D. So in this case, it is 1 centimeter times the power of 10 diopters is equal to 10 base down in the right. And in the left eye, H times D, 1 times 5 on this side is 5 prism diopters base down. Now people will get here, and now the last confusing part when you have two eyes working together is the net prism. And it's tricky, do you minus it, do you subtract it? Well, in vertical prism, you subtract the difference. And also, if it's base down in one eye, that's equivalent to base up in the other eye. So what I mean about this is I'm going to subtract these. So there's more base down in the right. So the net prism is 5 prism diopters base down in the right eye. But that is exactly equivalent, because it's all relative to each other, the eyes are relative to each other, to 5 prism diopters base up in the left eye. So again, great exam question, because you have to go from sphere cylindrical notation to power crosses, calculate the Prentice rule twice, figure out what the net prism is, and then understand that 5 diopters base down in the right is equivalent to 5 diopters base up in the left. All right. Great job. So we're 6 left. I think we're through most of the heavy calculations. So hopefully as we wind down here, your brain will get gently ready for sleep. Question 15. Precocious child named Little Mike Nguyen is a +2 diopter hyperope. Uncorrected, he can see from infinity to 10 centimeters. I want to know, what is his accommodative amplitude? It was like a 30-second question. All right, great job. Still getting that. Answer in this case is 12. One thing to be cautious of in these questions is infinity can be tricky. So we're talking about range of clear vision. If someone can see an infinity, but they don't tell you the refractive error. So if I'd left out the fact that it's a 2 diopter hyperope, and I said he can see clearly from infinity to 10 centimeters, what is the accommodative amplitude? The answer would be you don't know, because you don't know if he's using accommodation to get to infinity. So just be careful of that, because the roll call just thrown this out a couple of times in the last few years where they'll say, it's infinity to this, what is it? And the answer is you don't know. In this case, though, I gave you the refraction, he's +2. And so when you're calculating accommodative amplitude, you have to know kind of how much can they change the diopters in their eye. So at infinity, he has to use 2 diopters just to see to infinity, because he's a hyperope. And then he needs another 10 diopters to get to 10 centimeters. And so in total, his accommodative amplitude is 12 diopters. So optics of the human eye. This is the high yield for exam questions. One of them is refractive states and acquired refractive error. And I think it's popular because they've integrated optics now into other sections. So whether it's retina or cornea or plastics or the lid or peds, it can start with this person has acquired hyperopia or myopia, astigmatism, and then lead into something else. And so you need to be aware of kind of what can cause this, especially the stuff that can kill somebody, like a choroidal tumor can pushes the eye forward and causes acquired hyperopia. So if someone has a choroidal melanoma, the question might start as acquired hyperopia, or a baby has acquired myopia, might be congenital glaucoma, the eye's getting bigger. So this is often a lead into like an oral exam type question. Then there's accommodation, which they can just kind of throw around as of kind of tricky questions, and they can ask you about a bunch of different things. So concepts you kind of need to be aware of. One is far point, which is the point you're focused with accommodation completely relaxed. Near point is the point of focus with accommodation completely activated. Then range of clear vision is like where can the person see, far point to near point. And accommodative amplitude is the maximum increase in diopters that a person's eye can do, which goes down as you get older. And Albert asks, was a two-cycle given cycloplegic or manifest? Good question. Probably in this case, I think you'd probably say manifest if you're doing accommodative amplitude, but as long as they just give you a number for hyperopia, you can just assume that that's what they're using to see to infinity. Okay, 5 left. Question 16. What is the angular magnification of an emmetropic eye, power of 6 diopters as a simple magnifier? Is it higher or lower for a refractive mite? All right, so answer is C. Hopefully relatively simple if you know the concept, but magnification is tricky because there's a bunch of different types. So in this case, it's a simple magnifier. Power of simple magnifier is just, sorry, the mag is the power divided by 4. Kind of bizarrely simple equation, which is sort of nice. So the average eye is a power of 60. Divide that by 4 gives you 15 times, and it's at a reference difference of 25 centimeters. So it's basically saying is that when you look through a direct ophthalmoscope, the optic nerve, say, is approximately 15 times as big as if you pulled the optic nerve out of the eye and held it at 25 centimeters and looked at it. And then because it's power over 4, just refracted myope has more power, so you'd have a bigger number over 4, like 64, say, over 4, and so you'd get, if they're refractive myope, you get a higher magnification. Magnification is one of those things, I think it's high yield because it's confusing because there's a bunch of different types. And so it comes up, and it's just kind of an easy mathematical question to ask. So you have to be aware, one of the few things you have to memorize in optics is a number of formulas, and magnification has a bunch. So in lenses or mirrors, it's linear magnification, which is big U or big V, optic vergence over image vergence. Axial magnification is the linear magnification squared, and what axial means, took me a long time to kind of get my head around this, but if you think of the linear magnification of the optic nerve, if someone has, say, like papilledema, it's how high and how wide it is. The axial magnification is how much it's popping out, like how deep or how high it is. So axial magnification, like kind of depth, is the square of linear magnification. And then angular magnification can either be a simple magnifier or a telescope. For simple magnifiers, power divided by 4. And for telescopes, which we'll talk about in a second, it's minus the power of the eyepiece or the power of the objective. So good exam question, I think, just because there's a bunch of different types and you have to know which one they're asking for to know which formula to use. All right, question 17. Crystal has advanced retinitis pigmentosa. She's 20/20, but she only has a small central island of vision. Which visual aid is most likely to be helpful for her? All right, answer is Kane. Good job. A bunch of people got this. This is a these people get this wrong all the time, but I think people are getting up smart about it. So excellent job. Low vision has become just recently, I think, a very high yield question for the Royal College in particular. So let's just talk about it, and I think I'll try to give you a bit of an approach. Again, good oral question, good multiple choice question. So what the first thing when you think about visual aids, you want to think about it, I think, in categories, and that way you don't get yourself down the wrong path. First thing you want to think about is what type of vision loss am I dealing with? AMD, albinism is central vision loss. Their peripheral vision is fine. What they need is magnification, so they can, small letters, they can see. Peripheral vision loss, like retinitis pigmentosa, advanced glaucoma, they can see small letters fine. And if you magnify it, you're actually just going to make their peripheral vision worse. So they need orientation and mobility, like cane, dog, environmental. modification. So make sure you're thinking about the right type of visual aid. Second one is what people often will jump into, like sort of the opticsy ones, like the high plus, the magnifiers, the loops, the telescopes. Good to think about the non-optical aids first. That's always going to be part of the marks on oral exam in particular. And it's the one people tend to forget about. So it's another good exam question for that reason. So think about non-optical things, environmental changes, large text, cane dog, and then the optical aids, which is like the high plus add, the magnifiers, and the loops. And finally, near and distance aids. Most of the things that we talk about are mostly for near. So high plus adds, high plus classes, magnifiers, loops, all for near work. The only one really for distance is a telescope. I think if you think about it in that kind of categories, you're less likely to get yourself mixed up. And Anton asked a really cool question: would an inverted telescope be an option? The answer is kind of yes, in a way, although not really used practically. So he's basically just saying a telescope makes things bigger, but if someone needs some, if you flip the telescope over, it makes it smaller, and so it takes that central line and expands it. So technically, yes, although I don't think I've ever seen that on an exam before. Okay, so visual aids. Good way to think about in categories. And then another common question is like the pluses and minuses of each of those types of visual aids. All right, question 18. A 65-year-old patient has a visual acuity of 20 over 160 on the right and 20 over 120 on the left. What glasses should you give him to read 1M, a newspaper print, while maintaining binocular vision? +6, +8, +6 with 8 base in prism, +8 with 8 base in prism. Prem, you put a question mark in your answer. Answer is C. So this is another kind of a low vision, kind of high yield question, which is the Kestenbaum rule, which is this funky thing where you basically have an equation to give people glasses where they can read 1M print. I'm not sure why they use that, but it's kind of like newspaper print, approximately 2050 is sort of the standard, I guess, for low vision reading. And it's a nice simple equation. You basically take the visual acuity in their better eye and you flip it around. So this person had 2160 in the right and 2120 in other ones. You take the better eye, you flip it, and so it was like 20 over 20 there. 20 over 120 in the better eye. You just reciprocal that, and it's 6. So 6 diopters. Two things about this that I think are going to show up in exams just because they're tricky. One is that if the person is very young, if they can accommodate 6 very easily, let's say they're a 6-year-old with albinism, you don't need to give them glasses. The answer would be no, none, because they just accommodate and pull it closer. If you can accommodate that easily, you basically build in the lens into your own eye, and it's easier to do that than to give lenses. So just look closely. That's one trick they'll throw in. It's usually an older person, but if it's like someone who's 5 or 6 years old and it's accommodating 5 or 6, they can generally do it. The second part is if they're binocular. If someone who has +6 glasses has to read at the reciprocal of that, it's like 17-ish centimeters. That's very close. A lot of, especially older people, can't converge that much. So if they're binocular and they want to remain binocular, you have to add base in prism. Base in prism just lets them sit a bit exotropic up near. It's more comfortable. And this one's just a rule of thumb. The number is 2 more than the power. So if they have +4 glasses, you give them 6 base in both eyes. +6, you give them 8 base in both eyes. So Kestenbaum rule, flip the visual acuity in the better eye. Don't need it if they can accommodate it easily, and you add base in prism, 2 more than the power if they're binocular. All right, got 2 left. I was hoping to finish by 9, maybe slightly past that, I guess. Question 19. Telescope is composed of 2 lenses, +4 diopters and +10 diopters. What type of telescope is this, and what is the angular magnification? Feeling 45 seconds for this. Okay, I got two good questions here, so I'll just address those real quick before we go. Yeah, assuming 10 diameters is the eyepiece. Yes, absolutely. Question probably would say that, so it's a good point is we should point that out just to kind of make sure you're not flipping the telescope backwards. And Manso asks, should we assume half the accommodative amplitude of the previous question? That's a really good point. Thank you for bringing that up. So this refers to the previous question, but for the accommodation, if the question says reading glasses or using accommodation to read, you can just assume that the person can comfortably use half of their accommodative amplitude. It's a rule of thumb, but it is just kind of widely accepted. So unless they tell you otherwise, for someone to be comfortable, exactly right, they can only use half of their accommodative amplitude. So if they need to accommodate 6, their accommodative amplitude has to be at least 12 to make that comfortable. So that applies to low vision, but also reading glasses and bifocals as well. Okay, so this question, I think everybody got the astronomical part, but I think the Meg tripped some people up. So telescopes. I think kind of everything you need to know about telescopes can kind of be summarized, hopefully, in this just one table. So I'll throw that out there and we'll go through it. There's two types of telescopes: astronomical, Galilean. The way I think of it is kind of, I think if you think of it advantages and disadvantages, it's sort of the whole thing makes a bit of sense. So an astronomical has 2 plus lenses. And so this lens was a +4, +10, which makes it astronomical. The benefit of astronomical is you don't lose any light. The light all stays within the telescope, and that is why it's good for stars, right? It keeps all the light there. But in the trade-off, the disadvantage is that it's longer. So the telescope, the length between the distance between the lenses is the sum of the focal lengths. So it's a longer telescope. And the other disadvantage is you get an upside-down image. It's inverted when it comes out. The magnification technically is minus the power of the eyepiece over the power of objective. So in this case, it was minus 10/4 or minus 2.5. A Galilean is a minus eyepiece and a plus objective. So astronomical plus, Galilean minus. The disadvantage is you lose light. It kind of uses this fulcrum system, but light is lost. But the advantages you gain are it's shorter. So the distance between them is the difference of the focal length, and you get an upright image. Magnification, fortunately, the equation is the same. Minus eyepiece over power of objective. And because the eyepiece is minus, they cancel out and you get a plus magnification, so it's upright. That's kind of everything I think you need to know about telescopes. And this takes me to my last question. I thought it'd be kind of fun to play a matching game for our last thing here. On the left, I got a whole bunch of instruments or equipment that we use. And the right is the principle that kind of underlies it. And so I'm going to give you a 1 minute, and I want you just to match. This might be hard to put in the chat, but just match up each instrument or technology, whatever, to its underlying principle. Okay, and Prem managed to type the whole thing in the text, so hopefully that means we're ready to go. So let's go through each of these, and then I'll quickly show a diagram for each, and then we're done. So autorefractor, Schreiner principle. Coronal topography is Placido disk. Wavefront analysis is the Hartmann-Shack aberrometry. Applanation tonometry is image doubling. Direct ophthalmoscope, simple magnifier, came up before. Scanning laser polarimetry is retinal nerve fiber layer birefringence. OCT is interference, and loops are a telescope. All right, so let's go through each of these. This is the chapter on instruments in the AO manual. It goes through some of the descriptions, but I think the main thing is sort of that each has a principle that underlies it, and that I think is going to be the most common question. You know, someone once told me, and I think it's good advice, if you're in an exam and the person is asking you to, like, how do you construct a telescope? you've already aced that exam and they're just bored and they're just quizzing you to see kind of how much you know. So if you've gotten past the point of knowing the principle, you've already passed the exam, just drop the mic and walk out of there. But the simple principle behind each thing is a totally fair exam question. So how does the autorefractor work? Well, it's cool. A cool thing, I think it's Shiner, hopefully I'm pronouncing that right. If you have a double pinhole, when the light goes, if they're emmetropic, it goes to a single point. But if you're myopic or you're hyperopic, you get 2 points of focus. And so the thing just goes back and forth until it finds a single point of focus. That's how an autorefractor works. Corneal topography uses Placido discs. So it reflects these discs, these regular concentric circles on the eye, and uses that to analyze the topography of the cornea. Wavefront analysis uses a low power laser, shines it off the retina, and then the wavefront that comes back out, it uses this thing called a Hartmann-Shack screen to measure that, and it compares it to a perfect wavelength to kind of analyze the aberrations in your eye. Applanation tonometry, right? You ever wonder why it's like two semicircles like this? And the reason is it has a split field prism, or it's called image doubling, which allows you to measure precise distances in a target that is not stationary, it's moving. Direct ophthalmoscope, we sort of talked about, is just using the eye as a simple magnifier with the power of the eye divided by 4. Greater with refractive myopia, less with refractive hyperopia. OCT, such a cool instrument, is interference. It bounces light off the eye, bounces light off a mirror, and then those two cause interference pattern, and that's what it uses to analyze the image. Again, if they're asking you how it analyzes the image, you have already passed that exam, you are good to go. Just walk out of the room. And finally, loops. And loops, interestingly, can be either a Galilean or an astronomical telescope. I think this image is kind of cool because it kind of shows the advantages of both. See, the Galilean telescope is much shorter and gives you a erect image. The astronomical telescope, because it's the sum of the things, is longer and also requires a recting prism. So the astronomical telescope in loops is longer, but either can be used. And that, friends, is the end. That was a crazy whirlwind. Please don't feel too disheartened if that was tough. I wanted to make that feel like a bit of a beatdown. So hopefully when the OCAP comes, it won't be so much of a shock. So if you're feeling a little overwhelmed, just proud of you that you made it to the end and came out at all tonight. And I think my piece of advice to you would be to practice this stuff. It's, even if you get yourself marginally better, a couple extra marks, save some time, it's going to make a huge difference for your OCAP, and also just kind of long term, you're going to get these things down and help yourself through college, and I think hopefully kind of rich stuff for life. So I hope that was good. I'd love some feedback on how it went, and good luck everyone. It's I guess we're vague memories of the OCAP exam, but I remember it being stressful, so I hope it goes okay.
Yeah, well, what a great talk there, Mike. Very entertaining, most entertaining optics talk I've ever sat through. So I think there was a question in the session. You have so many.
Let me ask a combination. I'll have to swing back to that one, and
Okay.
I'll stick around if anyone has any questions. If I'm impressed that people are still awake and still here.
It's just the merits of the speaker.
No, congrats, Ed, on putting this together too. It's a impressive accomplishment.
Oh, yeah. So if there's still people listening that are in capacity to help out, I'm just getting a little old to do this. It's just the time that's involved. So if somehow, one person from each university would do it, we could rotate the speakers and stuff. Of course, we keep Mike Wan as the optics guy forever. But it would be nice. It's just time-wise, it's getting more difficult to arrange this. If it wasn't for Rahul Sharma and Ajelka Hannah helping out, I wouldn't have been able to do it this year. So, yeah. But, excellent talk. Like, it's well worth the effort of getting speakers like you, Mike. So.
Oh yeah, no, it's my pleasure. I hope it was useful. So maybe if it's okay with you, I'll just stick around. Someone's asking about the accommodation question, which is a very kind of high yield topic. So I thought I would just stick around and go through this one more time if I have a few minutes.
Oh yeah, sure. We'll just keep the line open. So we're trying to record this. If you email Yitka, maybe she'll be able to get the series to you. So it's Yitka Presta, the person you registered with.
Cool. All right. So thank you everyone for coming. Everyone, anyone who wants to stick with this question can stick around, or if not, please get some rest. Try to get some of that solidified in your brain. So this is the accommodation question. It sounds like this one was a bit confusing. So let's kind of go through this. So we'll go through this question again once more, and then just talk about the principles, and then feel free to ask any other questions. So in the question, I'm giving you that little Mike is a +2 hyperope. Someone asked about cycloplegic or manifest. Usually they won't make that distinction in this type of question, but it would probably be, there's like 5 different types of hyperopia, kind of a confusing concept. So I might just leave that for now because it's just going to confuse you. They'll just probably tell you hyperope, myope, emmetrope, that sort of thing. So I'm telling you it's a +2 hyperope, and then uncorrected, he can see from infinity to 10 centimeters. And so you have to say whether they're corrected or not, because that's really important. So in this case, he is +2 diopter hyperope, but he's uncorrected. He doesn't have glasses on. That means to get to infinity. So here's his range of clear vision, infinity to 10 centimeters. If he was an emmetrope, it would be 0 accommodation here, 10 diopters of accommodation here. So his accommodative amplitude would be, let's say this is emmetrope. His accommodative amplitude would be 10. But he's not, he's a hyperope. And what a hyperope, basically, if they're uncorrected, they have to accommodate just to see at infinity. So if you're a +1 diopter hyperope, or +2 in this case, you have to accommodate that amount just to get to infinity. So he's using up 2 diopters of accommodation to get to infinity. And then he has to add another 10 to get to 10 centimeters. And so that's why in this case, his accommodative amplitude is 12 diopters. Now, let's say I'll just change the question a bit to try to help us understand it if we kind of modify it a bit. Let's say I said corrected, he can see from infinity to 10 centimeters. Now it's interesting, if I give you a refractive error, but I say they're corrected, just treat them as an emmetrope now, because they don't have to, if they're corrected, they functionally act like an emmetrope, because if I give him +2, so different person, let's say this is Big Mike, and I say he's a +2 hyperope, but I've corrected him, and he can see from infinity to 10 centimeters. Because he's corrected, he doesn't have to use up any accommodation to see at infinity, so it starts at 0, and then he has to do 10 to get to 10 centimeters, so he would be a 10 diopter accommodative amplitude. Yeah, so good question. So it's tricky. Question, let's see, why, what is the range of accommodation? So if he's hyperope, why is accommodative amplitude increased? So it's a good question. I think it's not that the hyperopia increases the accommodative amplitude. It's basically just that he has to use up 2 diopters of accommodation and then do extra. So that means he has more. It's interesting. If he was an emmetrope and had the same amount of accommodation, 12 diopters, then he'd be able to see from infinity to 8 centimeters. But because he has to use up 2 diopters to see at infinity, he only gets to 10 centimeters. But the hyperopia isn't increasing his accommodative amplitude. That's just telling you that he's using up some to see at infinity and then using more to see up close. A good question. What if he was myopic, and what is the range of accommodations? Let's go to those questions too. Those are good questions. Let's say I said little Mike is a +2 diopter, sorry, -2 diopter myope. Let's change this question to say, let's say he's -2. He's not +2, he's -2. And then uncorrected, he can see from infinity to 10 centimeters. Problem with this question, if someone is a myope and they're uncorrected, they can't see at infinity. So the question wouldn't make sense. It would have to be the furthest a 2 diopter myope can see uncorrected without their glasses is 50 centimeters away. They can't see to infinity without their glasses. So let me change it to this. So let's say a precocious child is little Mike Nguyen. He's -2 diopter myope. Uncorrected, he sees from 50 centimeters to 10 centimeters. What is accommodative amplitude? In this case, I kind of do the same process. You're going 50 centimeters to 10 centimeters. A -2 diopter myope, when they're completely relaxed, they're not accommodating at all. Their eye just has 2 diopters of extra power built in here. So they're using 0 accommodation to see at 50. That's in their completely relaxed state. And then they're using 10 diopters to get to 10 centimeters. So if I said 50 to 10, oh, sorry. Let me fix that. So he's using, he's using 0 here. Mess myself up with this. And then he's getting to 10 diopters here. But he has 2 built in. So in this case, his accommodative amplitude is 8 diopters. Because he has 2 built in, and he's using an extra 8 to get to 10 centimeters. I feel like I might be confusing myself and everybody else with this situation. So it's more like he's got 2 diopters already built into his eye, and he has to get 10 to here. That's a better way to write it. And so his accommodating amplitude is 8 diopters, or if he was a myope. If I said he was a corrected myope, let's say he's -2 and he's a corrected myope, again, just if someone's corrected, just treat them as if they are emmetropic. So if he's a corrected myope and he sees from infinity to 10 centimeters, just forget about the refractive error and treat him as an emmetropic person. So infinity to 10 centimeters is 0 to 10 diopters. Accommodative amplitude would be 10. So sorry, I feel like this is why virtual is tricky because I can't see people's confused faces. We're going to go through it, but. And range of accommodation. So range of accommodation, I'll just do this for the original question. So when you're talking about range of accommodation, you're usually talking about where they see far to where they see near. And so in this question, you kind of given the range of accommodation. It's infinity to 10 centimeters. Now, technically, people would say, well, if you're a +2 hyperprobe, is it like, you know, +2, your focal point is kind of behind your head, right? It's like 50 centimeters behind. Think about range of accommodation is it only exists in the real world. We don't have like virtual ranges of accommodation. So if in this case, it has to be a real distance. So technically, if they have a virtual focal point behind them, it still just goes to infinity because it has to be kind of in the real world. Again, so I know this is a kind of confusing concept, so I hope I'm not kind of making things worse. All right, I'm gonna try to do a couple more here before I fade it. So what's why is the magnification -2.5 and not +2.5 with plus lenses? So the reason for telescopes. The telescope's magnification is minus the power of the eyepiece over the power of the objective. In an astronomical lens, they're both positive. So this minus goes in front of the eyepiece, which in this case was 10. Power objective is 4, and so it's -2.5 diopter, 2.5 times. That also kind of makes sense in terms of concepts. With astronomical telescopes, the image is inverted, so the magnification almost has to be minus, whereas with a Galilean telescope, the image is erect, so the magnification will always be positive. If you have 2 plus lenses, the minus part in the equation will always make the magnification negative. If you have a minus and a plus, like in a Galilean telescope, that minus in the equation will cancel out the other minus and it'll be positive. So for astronomical telescopes, this magnification is always going to be negative, and for Galilean, it's always going to be positive. Okay, for P convention, -2 over R. What decides if the R is negative or positive? That's a great question. It's like so many conventions in optics. So this is a mirror question. The person is asking. Page here. In mirrors, the technical definition is -2 over R. So the question is kind of like why is R positive? When is it negative? It's all the kind of conventions about how these things were first invented, but the R for a concave mirror is negative, and the R for a convex mirror is positive. And that just that convention I think was set up first, and so then because the power of the concave mirror is positive, but the R is negative, they had to throw this negative in technically to make the equation work. I used to teach it as just 2 over R and then would tell people, we'll just look at the type of mirror and use that as positive or negative. The reason I throw the negative in now is because I've seen questions on the OCAP where they ask you for the equation and it has a minus in it. So technically the minus is in there. When you're calculating, I think the easiest way always is basically just to look at the type of mirror. And if it's concave, the power is going to be positive. And if it's convex, the power is going to be negative. But the answer of why it's negative, the R is negative, is just pure convention. Memorize, that's fine. Yeah, pretty much. Let me see if I'm asking any more questions or. Yeah, it's getting kind of on the later side. So maybe listen, let me put my email up. If anyone has any questions, please feel free to email me. Optics is like my favorite thing. So I'm happy to answer any kind of email questions about this or if you have anything else. And that way, if anything else comes up, just fire away. So my email is michael.1@sickkids, all one word, .ca. So our residents kind of have an open line to me to write email any questions. And so anyone on the chat who wants to fire me an email, please feel totally free. And I'll try to fire you back an answer if I can. Anyway, thank you. That was cool. It was nice to see a few people on the call, and I hope that was useful. And thanks for putting this together. It's been cool to attend some of the talks and see some of the speakers, and so appreciate it. That's right. So I think I might be muted. Oh, you're muted, Edsel. Sorry, you talking?